Today in this video, I'm going to discuss about the parallel plate capacitor. Here we will calculate the capacitance of a parallel plate capacitor and vacuum in between the plates. In the next section, we'll discuss about the dielectric in between the plates. So we'll discuss the parallel plate capacitor. Parallel plate capacitor. And vacuum in between. That means there is no dielectric inside the parallel plates. So let's say there are two plates, and when it is connected to the any potential difference, one plate will be positively charged and another plate will be negatively charged. Let's say the left side, this is region 1. In between the two plates, this is region 2, and outside this, let's say region 3. And the distance between the plates is, let's say, small d, and according to the difference between the two plates, the distance between the two plates, d, is very small as compared to the area of the plates. Area of the plates means, let's say these are the plates. These are the plates. So these are the area of cross section. So d is very small as compared to the area of the plate. So what we can do, we can use the result that we have derived from the concept of the electric field due to a plane sheet, right? Charged plane sheet. So as a result, we have already derived that E is equal to sigma by 2 epsilon naught. This is the electric field for a single plate, right? For a very long or very large your charged plane sheet, thin sheet, right? So this is the electric field due to the sheet. Now, this one already derived. So we'll use the result because we'll think that we'll compare this result with this your plates, the electric field due to the plates. Now see, the electric field due to this plus plate, positive plate, right? Its density will consider, let's say, plus sigma is the charge density, and this is minus sigma, right? Now, due to positive plate, the electric field will be to the left in region 1, and in region 2, this will be to the right. Because by convention, we know that for a positive charge, the field lines are away, right? So this is what the concept of electric field lines. Now, due to the negative plate, the electric field lines will be, or electric field will be towards the plate. This is the electric field. This is the electric field due to the negatively charged plate. And this positively charged plate direction is also to the right side, and negatively charged plate also direction to towards the plate. So basically in region 2, this both the vector will be added, right? Both the electric field will be added in between the plates, and outside the plate, what will happen? Due to negative plate, the field lines will be towards, and due to positive plate, the field lines will be outside, right? Now they will cancel out. They will cancel out because they are same in magnitude, opposite in direction. They will cancel out. So region same in region 1 also. Due to positive plate, the electric field will be to the left, right, away, and due to the negative plate also there will be some effect of the electric. So the field is to the right. This is due to negative plate, or minus sigma, you can write better. This is due to the below line is this is due to minus sigma, and this field is due to plus sigma. Here same, this towards is due to minus sigma, away is due to plus sigma, and here the away is from for plus sigma, and this towards is due to minus sigma, right? But you think you can see here clearly that in between the plates, the electric field is in same direction, so the field will be added. So if we write the region 2, the electric field, net electric field will be your sigma by 2 epsilon naught plus sigma by 2 epsilon. Both are in same direction. So basically it is 2 times of sigma by 2 epsilon naught, which you can say it's sigma by epsilon naught. Right now in region 1 and region 3, no, there is no electric field will be 0. So region 1 and region 3, the electric field is 0 because due to one plate it is 2 sigma by 2 epsilon naught, due to another plate it is in opposite direction, so minus sigma by epsilon naught. So basically both will cancel out. No electric field in the outside region, so only inside region we have the electric field. Now what is our aim? Our aim is to find out the capacitance of the parallel plate capacitor. So these are two conducting plates. Parallel plates capacitor means capacitor consists of two plates, and these are parallelly kept, and they are of conducting plates generally. So the definition of capacitance is, is basically C equal to Q by V. It's a ratio of charge to your potential difference voltage. That means the charge accumulated over the surface and the ratio of the voltage provided. So more will be the voltage provided, more will be the charge accumulated. So the ratio will be a constant, and this constant ratio is called your capacitance. So our aim is to find out C. So here we got E in terms of sigma by epsilon, and also we know that sigma is the charge density. So in terms of Q by A we can write, so this is basically Q by A epsilon naught, right? So here we have the electric field. Now we are our intention is to find out the V. The relationship between E and V is your V equal to ED. V is equal to E dot dx integration. So if we'll integrate, it will get ED. D is the distance between the two plates, right? So if I'll replace this value of E from here, region 2 that we have derived, that is your Q by A epsilon naught, and D is here. So this is your V. Now what is our aim? To calculate the capacitance. So just I'll put the value of V here in your capacitance. So C equal to Q by V, and V is your QD by A epsilon naught. Q gets cancelled. So C is equal to A epsilon naught in the denominator. I will take it to the numerator, so it will become A epsilon naught by D. So this is the capacitance of a capacitor and parallel plate capacitor when there is vacuum in between. There is no dielectric or any other material inside the parallel plates. Now in the next section we'll insert or we'll add one dielectric in between the parallel plate capacitor, and we'll find out that how it is affecting the capacitance of the capacitor, how it will increase or how it will decrease the value of capacitance. We'll see the effect of dielectric in the parallel plate capacitor, that we will discuss in the next section. Thank you.